In 1937, Amelia Earhart and her navigator Fred Noonan vanished over the Pacific Ocean during an attempt to circumnavigate the globe. Their Lockheed Electra disappeared without a trace, and for 88 years, their fate remained one of history's most enduring mysteries. But in 2020, a man scrolling through Apple Maps noticed a strange object in the shallow waters off a tiny, uninhabited Pacific island. That discovery has sparked what may be the final chapter in the Earhart story. In the next couple of weeks, a team of researchers will travel to that remote island to investigate what they believe could be the wreckage of Earhart's long-lost plane. The Earhart discovery is just one example of how remote sensing is transforming historical detective work. This week, we're going off the radar with Dr. Leila Character, a Texas A&M geographer who uses these same tools to find lost World War II aircraft, shipwrecks, and solve mysteries that have haunted families for generations. From the depths of the ocean to images captured from space, this is the story of how remote sensing is helping us rewrite history. I'm meteorologist Emily Gracie, and you're listening to Off the Radar, a production of the National Weather Desk. On the show, we dig deep into topics about weather, climate, the ocean, space, and much more. Our goal is to help you better understand the weather and to love it as much as we do. On the morning of July 2nd, 1937, Amelia Earhart was about 18 hours into a flight that spanned over 2,500 miles. Earhart and her navigator Fred Noonan had planned on breaking up Earhart's trip along the equator into 34 legs, and this was the 31st leg. She'd already flown 22,000 miles. After this stretch of the journey, Earhart would only have about 7,000 miles left to finish her trip around the world. Her aircraft, a Lockheed Electra, was considered an ideal vehicle for long-distance travel, but it didn't have the range to cross the South Pacific without refueling. With limited options, Earhart and her route planning had chosen a tiny dot in the South Pacific called Howland Island, an island only 2 miles long and a mile wide. The island was so small and so remote that the Department of the Interior actually had to build a landing area on the island for Earhart when she mapped out her route. That landing strip approval came from her friend and supporter, President Franklin D. Roosevelt. A Coast Guard ship was to meet their aircraft at Howland Island with fuel for the next leg of their trip. But with the overcast skies that morning and a tiny landing strip below, Earhart and Noonan had to rely on radio communications to find the island and the even smaller Coast Guard ship from the sky. As Earhart and Noonan searched for the island, they sent a series of transmissions to the Coast Guard's ship, but the aircraft never made two-way radio contact. Earhart hadn't mastered the new radio equipment, so they couldn't hear what the Coast Guard might have been saying. It's likely that the Coast Guard tried to communicate via Morse code, but neither Earhart or Noonan understood the code system, a fact that the Coast Guard's ship members were unaware of. Time was of the essence. Earhart and Noonan circled the region where the island should have been. As their fuel levels continued to drop, Earhart brought the aircraft lower and lower. The Coast Guard continued broadcasting their position for Earhart's navigator, Fred Noonan, but he couldn't receive their transmissions. The Coast Guard even tried putting out clouds of smoke to signal their location, but the duo in the sky couldn't see it. Earhart's last message to the Coast Guard ship was registered at 8:43 a.m. Then, silence. For nearly 9 decades, Amelia Earhart's fate remained one of aviation's greatest unsolved mysteries. Theories emerged, expeditions searched, but the answer stayed out of reach, until an unexpected discovery in 2020 changed everything. Michael Ashmore was casually browsing Apple Maps when something in the shallow waters off a remote Pacific island caught his eye. It was an anomaly, a shape that didn't belong. He reached out to Dr. Rick Pettigrew, executive director of the Archaeology Legacy Institute, and what followed would reignite the search for Earhart's lost Lockheed Electra.
Careful analysis of the satellite imagery strongly supports the hypothesis that the Teraya object is in fact what remains of the Lockheed Electra 10 flown to Nikamororo by Amelia Earhart and Fred Noonan. In our sequence of images, it appears first on April 27, 2015. shortly after Tropical Cyclone Pam passed by in early March. It changes in appearance several times during our image sequence, most notably after other known storms. The measurements of the object in the images are very compatible with the known dimensions of the Electra.
Further analysis revealed it had been there all along, captured in 1938 aerial photographs and visible in 2001 helicopter footage as a metallic reflection beneath the water. Now, in partnership with the Purdue Research Foundation, Pettigrew's team is preparing to visit Nicomaroro next month. They're armed with nearly 40 years of accumulated evidence. Radio bearings that all point to this island. Human remains found here in 1940 that closely match Earhart's bone structure. 1930s artifacts and photographic anomalies showing what may be landing gear wedged in the reef.
The direct examination of the Teraya object on Nicomaroro will conclusively solve one of the greatest mysteries of the 20th century, the disappearance of Amelia Earhart and Fred Noonan.
An 88-year-old mystery may finally be solved, and the key was hidden in plain sight, waiting for the right technology and the right eyes to find it. This is the power of remote sensing. From LiDAR penetrating jungle canopy to reveal lost Maya cities, to sonar mapping shipwrecks in the deep ocean. These technologies are rewriting what we know about our past. They let us see the invisible, uncover the buried, and solve mysteries that once seemed unsolvable. Our guest today has devoted her career to exactly this pursuit. Dr. Leila Character is an assistant professor of geography at Texas A&M University, where she uses satellite imagery and machine learning to locate World War II aircraft wreckage underwater, identify ancient Roman burial mounds, and map uncharted seafloor terrain. Her work sits at the fascinating intersection of history, cutting-edge science, and computational technology, and it's bringing closure to families who have waited decades for answers about loved ones lost to war and tragedy. Dr. Leila Character, thank you so much for talking to me today about this really, really fascinating field. I mean, people think weather is cool, but this is next level. This is like something movies are made of. Aerial archaeology, this is a term I wasn't even familiar with until a few weeks ago when I started maybe taking too deep of a dive into the Amelia Earhart case. But this is really fascinating. And I found that there are people like you that study this really interesting area of expertise. So give me some background on you, because I'm also curious, somebody who does this for a living, like what your background is, because it seems very kind of multidisciplinary.
Yeah, that's totally right. And it also is like very happenstance. I wish I could say that my path has been deliberate, but it hasn't been. It's been like a series of coincidences that has led to me working on something I find fascinating. So I went to college, got a degree in geology. I worked for a while. Then I decided to go back to graduate school. And I went to graduate school for something that was like a combination of geology and archaeology, aka geoarchaeology. At the end of my master's degree, I was doing some caving in an archaeological area of Guatemala because I have a background in caving, and we were looking for a cave that maybe contained a climate record that would help to explain some of the demographic changes of the Maya around this area. And it was a lot of work. We were looking at LiDAR imagery and trying to identify areas just manually that like might contain caves. And then we'd like walk for like 12 kilometers and machete our way through the tropical forest and not find a cave. That was pretty inefficient. So I had a little bit of like background in remote sensing, a little bit of background in GIS, definitely no machine learning. And this is like during my master's degree, I turn around to someone while we're walking in the forest and I'm like, hey, do you think machine learning would do a better job with finding caves than we are? And he was like, what are you talking about? Like, I'm hot. A mosquito is like, like mosquitoes are attacking me. What are you talking about? But actually, after he got past that, he was like, that's really interesting. Like, I don't know. You should see if anybody's working on it. So I went back to Texas when the fieldwork was done and discovered that it actually like was not so wild, the idea of using machine learning to predict cave entrances. So I did that. And that worked like, okay, like that was like, it worked. I'm not going to say great, but it like worked okay. Like we went and checked, validated the results in the field, found some caves. And right around that time, when I knew that it was like working okay and I was interested in pursuing this, and this is pretty exciting, an archaeologist got in touch with me and was like, hey, like the cave stuff you're doing is interesting, but what would be really neat is if you could use your approach, the approach that you've developed, and find ancient Maya features in my study area. So I was like, okay, I mean, that sounds interesting. Like, sure, let's try it. Like, I have some archaeological background. I'm in a lab group that's really focused on Central America and Mexico and the Maya. So I did that. And that became one of my really big and kind of ongoing projects. From there, it kind of carried its own momentum. Like, I applied to do some work with the Navy, and some funded work with the Navy. And I didn't have a specific project in mind. I just told them my skill set. And I got like a call from an unknown number one day, and it was someone from the Navy's Office of Archaeology. And they were like, hey, like, we saw your project with the Maya and the caves. What do you think you could do with shipwrecks? But it's all just been kind of like self-propelling, because I'm not an archaeologist, but I have archaeological background and I know a lot of archaeologists. And it's just like I have this skill set and I like a really good challenging problem, and I like to address it. I like existing problems that somebody wants to be solved, but they don't have the skills to do it themselves. And I work on land, I work underwater, and that's me.
Have you ever watched Drain the Oceans? National Geographic's Drain the Ocean. Have you been on Drain the Oceans?
I haven't been on Drain the Oceans, but somebody that I work very closely with has been on Drain the Oceans.
That was like one of our favorite COVID shows. We watched all of them, my family. Okay. Let's go back to the Navy getting involved and shipwrecks, because did this also lead into you looking for World War II planes that went down in the ocean?
Yeah, I did the World War II aircraft project is ongoing, but it started as my postdoc like research project. And that, again, like very self-propelling. Like somebody at the Navy told somebody at University of Delaware that they knew what I was working on with shipwrecks, and the person at University of Delaware was like, great, I need a postdoc that can work with my group on World War II aircraft. It just fell into place, and it's been a really good fit. It's been like a way to kind of continue developing my skill set. Sometimes I collect imagery myself. Sometimes I don't. Sometimes I'm using typically not satellite imagery because it's not high enough resolution, but sometimes I use imagery that other people collect, like with an airplane or with a drone, or with a ship. But the World War II project is data that we collect. Like I go out there and collect it with a small team, using like underwater drones. It's cool.
Okay.
It's a cool
project. So are you in a ship or in an airplane when you're doing that?
When we do that, generally we're in neither. So we are the sensor that we're collecting data with is a side scan sonar sensor, and that's mounted on an underwater drone. So it's fully autonomous, and we can launch that underwater drone from just like a little boat or a ship. Occasionally we do it from a ship.
Okay. Now, anecdotally, can you share some situations that you've been in where you've like discovered something and what that's like?
Yeah. So I'm not going to go into a specific location because the reason we're looking for these aircraft is it is DoD funded. And we are looking for aircraft that contain the remains of missing in action American service members. So for that reason, just so that I don't, share too much, I'm not going to say any locations, but I'll talk to you a little bit about a couple of the things that I've been part of finding. So the last couple of years, we have found aircraft that we have matched up with a missing American service member, and it is pretty crazy. So I do, like, part of what makes me a little bit unique, I think, is because I have an archaeological background, a geology background, and fieldwork. I'm generally like full circle part of the project. So I help collect the data out in the field. I do the machine learning, and then I validate the results or ground truth the results. So with World War II aircraft, that means I'm diving. So, like imagine finding something that looks like an aircraft in sonar. Not imagine, I mean, this is the way it works. So, let's say last summer, we collect sonar and we go back and we're looking at the sonar and it looks like there's an aircraft in the imagery. And, but we never know what we're looking at until we dive, or if it's an American aircraft or from some other place. Some of the places we work have, Japanese aircraft, for example. And sometime in this summer or the previous summer, I was part of the first team to dive on one of these aircraft that we wanted to ground truth. So everybody on my team is really, really good at identifying aircraft, what type they are, whether they're American or not, except me. I'm like much newer to it than everybody else, and I'm really focused on the computational aspect. So I dive, but I'm not, like I can't look at like landing gear and tell whether or not it's American, or I can't look at the nose cone that's on the front of a propeller and tell whether it's American. I go down with one other diver and we come right down on this aircraft, and like immediately I can tell it looks different. This is the first American aircraft I'd found. Like I can tell that it looks different than things that I've seen before.
When you say dive, is it scuba dive or
scuba dive? Yeah,
okay.
Scuba dive.
How deep is this?
We don't go past the limits of recreational diving typically. So about 140 feet or 40 meters.
Okay.
And this was probably close to that. We're often kind of like at that. The things we find are not all, but often around that kind of like 100 to 120. I like looked over at my dive partner, because I was like, this looks a little bit different, but I don't know. And he's just flapping. He's like he has like oxygen or air in, so he's he can't like talk to me, but he's excitedly flapping at me, which I interpret correctly that A, it's a plane, and B, it's what we're looking for. And then we have a great team where we provide some identifying features, and then we get in touch with our historian, and he provides the like confirmation that it's what we're looking for. Sometimes that's really complicated. Sometimes we know right away, but it is incredibly, incredibly exciting. It's really hard to find this stuff. I mean, the ocean is a huge place, and we're just surveying like small parts of it at once. Generally, we have like 2 underwater drones or autonomous underwater vehicles running at the same time, and they each can survey like 2 square kilometers a day. So, that's not like that big in the scope of the ocean. So it's really hard to find this stuff. It's like a needle in a haystack. So when we actually find someone that we're looking for, and then they can be brought home and their family has some answers about, the uncle or brother that just like disappeared. That's exciting. And it's also exciting from a tech point of view. Obviously, I'm really fascinated by the remote sensing and the machine learning. That's where I get really, really excited, is like making these methods work to do something in the real world, like find someone.
Yeah, that has to be very rewarding. Do you ever hear from the family members?
Yeah, we get invited to the funerals. Unfortunately, it was on the first day of class here, so I couldn't go. But there was a funeral in August of somebody that was repatriated thanks to the team's efforts. So I would say we always hear from the families, actually. And in fact, I was on a letter to a family member from someone that we found this summer. So they're notified, and I think we're always in touch with them. It is. My family doesn't have that military background. So it is interesting, and I think even surprising that, all these years later, like they always care. Nobody is ever like, why are you telling me this? Mm-hmm. Like everybody is always pretty like invested to know where they went.
Yeah. Wow. What about the shipwrecks? What kind of shipwrecks have you worked on or looked for?
So the Shipwrecks project does not have any it doesn't have any field work with it. Unfortunately, all of this work underwater gets more challenging the deeper you are, because that can affect the quality of the imagery, especially if there's like particles reflecting in the water or it's turbid. So the Shipwrecks project, I actually used a bunch of publicly available data that was not data I collected myself. NOAA collects coastal bathymetry or underwater topography data for all kinds of purposes, like coastal flood monitoring and nautical charts and things like that. And there's also like a publicly available database of underwater obstructions that includes shipwrecks. So I used those data as well as some data that the Navy gave me that were confidential, and made a model to find shipwrecks that worked pretty well. But I definitely the database contains like 15,000 shipwrecks. And some of those coordinates are not good or in the wrong place, or sometimes the bathymetric data of the seafloor is just too low resolution. So it's like a blurry photograph, and it just doesn't work. So that project took place around the entire coast of the United States and Puerto Rico. So a really, really huge area. And because I didn't dive in on any of them, I can't say for sure what we were finding, but based on the database and some of the information it contained, I think often they were metal wrecks. I think that like older wooden shipwrecks, their preservation depends on a lot of things like the depths. I mean, if things are too shallow, then they just get like torn up, but like the depth and the sediment conditions and the water temperature, etc. But this is actually, so I'm at Texas A&M now, which has probably like the largest and like most active nautical archaeology department in the country. And I'm having some meetings with a nautical archaeologist that works all over the world who has a bunch of multi-beam sonar data and side-scan sonar data. And I think we're probably going to start back up working on the shipwreck project because there's like a lot more shipwreck data than aircraft data, a lot more ships underwater overall than aircraft. They're also easier to find because they're much bigger. So I think there's a lot more to do with that. And I think that the project with this guy that's here at Texas A&M, that will probably focus a lot more heavily on ancient shipwrecks, actually, not modern shipwrecks. So that'll be exciting.
Yeah. Wow. When it comes to the machine learning, can you describe in a way that like the general person might understand how you can use machine learning to turn this data into something that finds you a cave or finds you a shipwreck?
Yeah. The way that machine learning works, let's just use the example of shipwreck, is that you have, for me, I only do machine learning with remotely sensed data. So that's like multi-beam sonar, which provides like a bathymetric or topographic map of the seafloor. And it's like an image. It's basically like a picture. And the picture is composed of individual pixels, and each pixel contains an elevation value that corresponds to a specific elevation value on the seafloor. And with machine learning, you have, that picture of the elevation of the seafloor, and then you have known locations of shipwrecks. So you have to have the imagery, and you have to have some known locations of whatever you're looking for. So in this case, the example is shipwrecks. And you put those shipwrecks on top of the elevation image, and you say like, hey, like these elevation values characterize are like a good description of shipwrecks. And these elevation values are not. It's just background topography. And if you have lots of examples of shipwrecks, then you can teach the machine learning model iteratively by feeding it this data. Like these are the elevation values associated with shipwrecks. These are the elevation values not. And you go through again and again and again. But like instead of just having elevation values, you'd have other variables as well. So there are like a lot of different factors or parameters that you can derive from elevation, like slope, for instance, or how rough a given surface is. Quantitatively, and all of those parameters can be fed into a machine learning model kind of in a stack. The model just learns this really detailed representation of these numerical quantitative values that are associated with shipwrecks. And then when you feed it a new image of elevation values with no shipwrecks, it says like, hey, based on what I learned from all these examples you gave me of shipwrecks, I think there's a shipwreck here and here and here.
When it comes to weather and like weather systems like hurricanes or tropical storms, I can imagine that plays like a role in maybe stuff moving around, especially shallower. And that seemed to be that's like the suspected case with the Amelia Earhart possible plane. Is that things may have been stirred up. Have you noticed that before, where like tropical systems stir up things and then all of a sudden something's uncovered that you didn't see before?
Because everything we're looking for is like, it's unusual that we find anything under like 60 or 70 feet, more shallow than 60 or 70 feet, maybe partially because others would have found it before. I don't think specifically we've experienced that things get uncovered, but we have experienced directly that, weather and currents and wave patterns can affect how things sink once they hit the water. So, for example, when we go places to find aircraft, the reason we're going is because there's some kind of historical account that suggests someone we're interested crashed. in that location. And those historical accounts often include like the date, the weather, a coordinate on the seafloor, sometime a coordinate on the sea surface of like where the aircraft was last seen, which, it's all word of mouth. So who knows? But, I think like after these aircraft crashed, they were interviewing other people that were flying, interviewing people on land. And there's this like folder file associated with the aircraft crash. And sometimes we actually get into a GIS system and we plot all this information about how far they were from the coast and where their last known position was. And then we try to figure out that at that time of year, which way was the current going? What was the weather doing? What was the wind doing? Because probably if things didn't sink immediately, they probably moved, like even as they were sinking. And sometimes things move a lot. Like some of the currents in places we've worked are like crazy, crazy fast. We did some work off the coast of West Africa a few years ago. And those currents are like ripping. So that's going to heavily affect, if not burial of things, like where we actually find them. Like where did they go into the water, but where did they move before, go landing on the bottom?
Wow. Yeah, and I can imagine with the shipwrecks, like the cause of those is probably like a lot of the times weather related, right?
Yeah, I think that is definitely, if it's not like a wartime thing, then yes, I think it's like weather or obstruction related.
Are there any like old mysteries that have been unsolved that you would love to get your hands on?
Well, I mean, I think maybe this isn't as exciting as you're hoping, but when we survey in the North Pacific, we often end up seeing these like circular features, like it's like really, really common. When we're surveying, there's just like these big circular features, and there's often like many of them in our sonar, and we don't know what they are and are intrigued by them. And I recently saw a French research team, but actually found circles that look pretty similar to what we have. And they're like a really unique coral community that is not something that's been previously documented. I don't think we have the same thing. But when I saw that they saw those circular features also in side scan sonar, and then they went and checked them out and, dived on them, I was really intrigued and was like, maybe we should look into this further and see what we're finding. Sometimes it's just impossible to tell what you're looking at in the side scan sonar. And it would be really interesting to know if it's a similar, like really unusual biological community, which obviously is not my area of expertise, but I always work with someone that's focused like on the subject matter, like an oceanographer or somebody that focuses on underwater ecology.
I can imagine, and maybe this isn't the case for you because you seem like very scientific, but I can imagine like if you were excited about something that you wanted to find, like that balance of like, is this really what we are looking for or is it not? Like, do you ever have that bias of you want this to work out?
I think we all do. I think like, everyone that I work with, like every time we go off and we're looking for a different aircraft, we're like, we're going to find it. We've got it. And then, every time we find an aircraft in the model, we're like, this is it. This is the one we're looking for. And I mean, it's hard not to feel like that. It is exciting. And we spend a huge amount of time preparing and invest a lot of time and money. So, I think that's the way. I mean, you couldn't do this work if you weren't like by nature positive and not easily discouraged, So there definitely is a lot of that feeling. And it is like, when you go in ground truth, you really want, and you really, really want, I mean, there's two. There's like, number one, you want to find the planes because like we're there looking for people. But with any of the machine learning that I do, I just want it to work, like I want it to like actually correctly predict the things it says it's predicting. So I'm often invested like in multiple layers from the human sense, but also from the computational sense. And I mean, it is exciting. I wouldn't do this stuff if it weren't.
Yeah, it's a really cool field. It's interesting, though, because I think that for most of my life, if somebody said, like, describe archaeology, all I would picture is, like, somebody with, like, a little brush getting dinosaur bones out. But this is next level. Like, this is very cool the way things are done now. But we've mostly been talking about stuff over water. Are these same, like, remote sensing tools used over land, too?
Yeah. They are. And I have, like, several land-based projects. One in Romania that's identifying burial mounds. And then the Maya project that I already mentioned that's in Central America and Mexico. And you can use this like that same methodology. You have to have a different type of imagery. So instead of like multi-beam sonar, LiDAR, or some kind of color imagery, spectral, multispectral, or hyperspectral imagery specifically. But interestingly, the complicated part is actually not the machine learning. It's getting the imagery and getting the training data and then manipulating the imagery so that it will show you what it's looking for. And then, like all of this, it's I think archaeology still like the way that people are making new discoveries and really moving the field forward is still through like excavation, among other things. But I think what machine learning really adds is it's a really like comprehensive and efficient way of surveying in places that maybe have never been surveyed before. And then the results of the machine learning model can help the boots on the ground archaeologists to go and make their time on the ground really efficient by just going to where the machine learning model has made predictions and, going from there with your more traditional archaeology.
Less of the machete in the jungle type of work.
Yes. Yes.
I wanted to ask you, you mentioned climate record. And, we often think about like tracking climate both through like ice cores and tree rings. Are there other places where we can track climate?
Yes, through caves. When you have a cave, and it's like a calcium-rich cave, most caves are in a limestone type of rock, which is calcium-rich. In wet caves, there's a lot of moisture. And as that moisture, condensates on the roof of a cave, it drips. And if that drip is calcium rich, then it forms a stalactite over time. That's like a kindergarten explanation. That's like probably not even fully correct. And that stalactite, because as it forms, the water that forms it captures like the ratio of different types of oxygen. It like forms in individual layers. And those individual layers actually can provide a very high resolution climate record of whether the climate was warm, dry, wet, or cold based on oxygen and hydrogen values that were in that water at the time the stalactite formed.
Cool. You must just be like a history buff too, right?
I like old things. I joke about like I really like old stuff. Like anything old. It doesn't have to be like nice. It can be like a house that's falling down and I'm like, oh, is this house old? Let's go look at it. Yeah, I like old things. History included.
What do you think the benefit is of like solving old mysteries and going deep into history? How does that help us in the future?
All of this stuff that I'm looking for that machine learning helps to more efficiently find and to comprehensively map means that we can understand patterns across the landscape, which, if you're just like walking around on the ground or diving underwater without the assistance of machine learning and remote sensing, you're just going to have this like really piecemeal map. But instead you have this like comprehensive map, which means you can study patterns and relationships between things. And that is critical for understanding why something happened the way that it did.
Well, it sounds like just like with weather, no matter how advanced the machine learning gets, there's still that need for field research and boots on the ground.
Yeah, definitely. Yeah, it starts and ends with boots on the ground.
Dr. Character, is there anything else you want to add about your work?
My undergrad was in geology, and then I went to get a master's degree in geography, having never heard of it. I didn't know what it was. I just like somebody was doing something cool and they were in a geography program, and I am still in a geography program. So if somebody like listens to this podcast and they think remote sensing and GIS and geospatial analyses and machine learning and this whole interdisciplinary thing is important or exciting, they should consider geography, because nobody has ever heard of it. Nobody knows what it is. It's not like like state capitals or anything like that. I don't even make that many maps. I make maps, but like not that many. You can do some cool stuff.
So it's a broad field.
It is a broad field. I will add, to go with the first thing you said to me, that what I do is incredibly interdisciplinary and requires all different kinds of people working together. Like that kind of collaborative interdisciplinary work is important now, and just increasingly important in the future as the world becomes smaller and smaller and smaller.
Off the Radar is a production of the National Weather Desk. Make sure you're following the show on Apple Podcasts, Spotify, or wherever you listen to podcasts. New episodes publish every Tuesday. Thank you to Dr. Leila Character from Texas A&M for joining me today. The sound bites you heard at the beginning of the episode from Dr. Rick Pettigrew were provided by the Purdue Research Foundation and the Archaeology Legacy Institute. This episode was produced and edited by myself, with writing help from associate producer Brian Petrus. Thanks to the National Weather Desk and Sinclair Broadcast Group for their ongoing support of the podcast. I'm meteorologist Emily Gracie. Make it a great day.